Hello everybody. Okay, so today we're going to be looking at full symmetrical parabolas. Now, in our notes, we've already looked at how to look at two-dimensional motion along an incline. We can consider it linear if we remember to take any acceleration along the incline and break it down and use the piece that's parallel to the incline. We practiced doing that, even the diagrams. All right, then we looked at half parabola projectile motion, and we've been practicing a lot of that, haven't we? So today we are going to do full symmetrical parabolas, and once again I'm going to kind of color code this stuff because it just simply visually separates it better. But again, I'm going to use blue for horizontal. In fact, let me just put it right. Let's just put it right here. Okay, so blue is the x-plane motion, and I'm going to use green for the y-plane motion, and I'm going to use red for resultants or anything else like that. Okay, the combination of the two. All right, so what I have drawn here is a horizontal stretch of land, and there's a ball, and somebody kicks the ball, and it follows a parabolic trajectory, okay? Follows a parabolic trajectory. That's what we call the direction of the path. We call it the trajectory, so make sure you know what trajectory means. Now, we're going to be looking at several points along through here. So I'm going to just mark some of those points. Obviously, we will look at the point at the very top of the parabola, and of course the point when we get to the bottom, back down on the ground, okay? And let's look at some other points in between. We'll look at one right here, I guess, and maybe one right here. All right, so two sort of spaced out there, and we'll look at two more kind of spaced out at the same similar locations right there. Those are good. And of course, here's the ball at its initial point. All right, now remember, when you kick a ball, it's not a projectile until it actually leaves your foot. When it's no longer in contact with your foot, then it's a projectile, because at that point, with no force from your foot acting on it, the only force acting on it would be gravity, so it would be in free fall at that point, and then it will be a projectile. Once it reaches the ground over here and the ground acts on it, again, it would be no longer in free fall, so it would no longer be a projectile. We're not looking at that either. So only from the point where it leaves the person's foot to the point where it strikes the ground do we consider the projectile motion. Now, let's start with the fact that in this case, the ball has to go up before it can come down. So when it leaves your foot, it has some initial velocity tangent to the motion. Okay, there it is, the initial velocity. That velocity is at some angle. If we look at the center point of the ball, it's at some angle theta to the horizontal. And basically, we can take that initial velocity if we know it. If we know the magnitude and the direction of the initial velocity, we could use our vector resolution skills to resolve this velocity into an initial x component and an initial y component. Cool beans, right? In fact, we know how to find those two pieces, don't we? V sub O x would be the hypotenuse times the cosine of the angle, since it's adjacent, right? And V sub O y would be V sub O times the sine of the angle, the hypotenuse times the sine of the angle, since it's opposite the angle. All right? Now, however, what if we don't know the initial velocity and its trajectory angle? what if we want to find those? Well, you'd have to use what you know about the kinematics of the two motions, and if you don't know them, you'd have to determine these two initial components. If you know those two initial components, then we can add them together like we would any two perpendicular vectors. We would say v sub o equals the square root of the x component squared plus the y component squared. All right, that would give us the magnitude of the hypotenuse, and then the direction above the horizontal would be the inverse tangent of the tangent ratio, which would be the vertical component over the horizontal component. Just like when we added regular perpendicular vectors, okay? Only this happens to be perpendicular vectors for a projectile, but the idea is the same. So, if you know the initial velocity and the angle of trajectory, you can resolve it into the two components. If you know the two components, you can add them, like we do any two perpendicular vectors, to get the magnitude and direction of that initial velocity, okay? Now, let us look at the other side. Oh, well, no, wait, let's wait on the other side for a minute. Let's actually go ahead and talk about the two independent motions of the projectile, the horizontal and the vertical. And just like last time, we will talk about the horizontal first. So, what happens to the projectile's horizontal velocity during the trip? Well, as you know, once it leaves the foot, there's no force acting on the projectile except gravity. Since gravity is vertical, it is independent of the horizontal velocity and cannot affect it. So, since there's nothing to affect the horizontal motion, it stays constant. So right here, we're going to say v sub x remains constant. That's how we would say it in English. The velocity remains constant. The x-plane or horizontal velocity remains constant. Now, mathematically, if we want to do it, we would look at the general equation. Okay. Oops, that's supposed to be an x right there, sorry. But as you know, the horizontal acceleration is 0, so that drops out. And if we take the initial position where the ball starts over here horizontally to be 0, because we usually start measuring distance at 0, then we get constant velocity formula. Our final position, or the distance we travel, is equal to v sub ox times t. All right, so now we know that this horizontal velocity stays constant, so I'm just going to redraw this velocity all along through here, just the same size as it is right there, or at least do my best to do that. Okay, here it is. It's not going to change at all for the entire trip. It's going to stay exactly the same. And when it strikes the ground with a horizontal velocity of v, if you will, v sub fx, which is the same value as v sub ox. It hasn't changed. Okay? The displacement it travels, if you take x sub o to be 0, and it ends up over here, so it travels a displacement we'll call x sub f, if we take x sub o to be 0, and we call that the range, remember? Okay. Now, the horizontal acceleration we said is 0, and are they ever going to remind us of that in a problem? Of course not. They're not going to make our lives easy for us. We have to learn this information ourselves. We have to understand it from the physics of the motion. So, make sure you remember that. And all of this takes place in a time we'll call t sub x, if you will. All right? So we've got our horizontal distance. We've got our initial velocity, which stays constant. We've got our horizontal acceleration and our time, d, v, a, t. So that's our 4 variables. Okay? We even have vf over here. It's the same as it was over here. Okay, so that wasn't so bad, was it? All right? Now, let's go ahead and talk about the vertical motion a little bit. Now, this is going to be a little bit different. Why? Because unlike the half parabolas, which started at the top and came down, we only saw this part. These go up first before coming down. So we've got 2 directions being traveled. Now, because we have 2 directions in our plane of motion, remember, they can't both be positive. So if you have some vectors that point up and some that point down, we need to determine what are we going to choose for directional signs in the vertical plane. Now, as we've been doing, I'm going to choose up to be the positive direction and down to be the negative direction. Okay? So as the ball starts with its initial vertical velocity, as it travels upward, that initial vertical velocity decreases in value until when you get at the top, the vertical velocity, the y velocity at the top, is 0. Because just for an instant, it pauses vertically. Now, does that mean it stops moving altogether? Heck no, look at that. It's still moving horizontally at the top. Okay? All right? Now, as it comes back down, again because of gravity, instead of decreasing by increments of 9.8, we're going to add increments of 9.8. But Miss Pepitone, how can you do that? You said that down is negative and 9.8 meters per second squared points down all the time. Yeah, but look at your velocity. It's also now going to point down also. So you're going to be, instead of taking a positive velocity and subtracting increments of 9.8, you're going to take a negative velocity and subtract increments of 9.8, which is going to increase it. Okay? Until when you get down here, when it strikes the ground, it will have a final y velocity. Now, is there anything special we need to know about that final y velocity? Well, if we subtracted out 6 increments of 9.8 and then we added them back over here, then this final velocity magnitude should be the same as the initial velocity magnitude. It just points down instead of up. So right here, these 2 magnitudes will be the same as long as it's a full symmetrical parabola. These 2 magnitudes will be the same even if their directions are reversed. Okay? All right. Now, as we said, we are decreasing our velocity and then increasing again by increments of negative 9.8. So let's write that down. Our vertical acceleration is going to be the acceleration due to gravity, and that's going to be negative 9.8 meters per second squared. And are they ever going to tell you this? No, of course not. They expect you to understand that because it's in free fall, only gravity acting on it, then it's going to have that magnitude acceleration, and as long as you let down be negative, then it'll be a negative acceleration. All right, so let's answer this question right here before we go on. What happens to the projectile's vertical or y velocity during the trip? Well, what did we say it happens to it? It decreases upward to a stop and then increases on the way down, right? So let's write that. That's all you have to do. You write it exactly as you describe it on the picture. So the vertical velocity decreases Okay, you decrease the y velocity upward to a stop right at that tippy top point. Then increases downward. Okay? Now, what if we wanted to describe it mathematically? That's the English, but let's do just like we did up here. English, math, English. What about the math? All right, let's look at the general equation. We get y sub f equals y sub o plus v sub o y t plus 1/2, and you can put ay for now, t squared. Okay, boy, I just barely squished that in, didn't I? All right, now if we take the initial position vertically, what do we usually take for the ground? 0, right? Because the ball can't go below ground, so we'll take 0 to be on the ground. All right. Oh, but where does it end up? Back on the ground. Its final position is the same. Okay? It ends up back on the ground. So the final position is the same as the initial, so you have actually no overall vertical displacement for a full symmetrical parabola in the y-plane. No vertical displacement at all. Okay? Now that doesn't mean the ball doesn't travel a distance. Yes, it travels so far up and so far down. It's the same each way. Okay? Now that means what you can do is, if you bring one of these over, you can say v sub o y t, and one of them has to change sign. It doesn't really matter which one, but I like to put it on this one because we know the g is negative. So you get 1/2 g t squared, and I'm going to make that positive now, because if this is a negative and this is negative, the two negative times a negative is a positive. Okay, so that's how we'll end up with a positive value right here. Okay, next, what happens? Oh, look, a t cancels out on each side. So what expression are we going to be left with? Oh, the initial y velocity equals 1/2 gt. Okay, because this t cancels with one of those two, leaving one behind. So look what's happened to our general equation. It's down to this now. Isn't that kind of interesting? But I wouldn't memorize that. That's a big mistake. Memorizing special case formulas is a big mistake because there can be so many special case formulas. Just remember this. You start with this and think, oh, but I know these two are 0. And then go from there yourself, okay? All right, now let's go back to our picture for just a minute. Okay, we've looked at what happens to the vertical velocity, and here's the vertical acceleration. We also just said that the overall vertical displacement for the entire trip is 0. And they're never going to tell you this. So put a star beside that. It starts vertically at the same point it ends up. It starts on the ground, goes up, comes down, ends on the ground. They're never going to tell you that. They're going to expect you to understand that from the fact that it's a full symmetrical parabola, like a golf ball, or here like maybe a soccer ball. So guys, that's another place. So we have 1, 2, 3. We have 3 inferred pieces of information. And notice they're not necessarily the same as for a half parabola. So that means there's a difference, and you have to be aware of that. Now, one of the things that we will be learning to do is we will also be learning to determine how high does the ball go to get to the top of the parabola. Okay? So we'll call that h, the height. Okay? We'll be learning how to figure that out. Finally, all of this motion takes place in a time we'll call t sub y for the vertical motion. But how are those two times related? Well, The ball doesn't go horizontally, back up, and then go up and down. It does both motions at the same time. So that means these two times are the same. And remember, we call this the hang time. It is the same for both, but the vertical motion is what controls the time it takes to go up and down because of the acceleration due to gravity. It just happens that while it's decelerating up and accelerating down, it just happens that it's also going forward. All right, but the two motions are independent. So however long it takes it to go up and come back down, that's the only amount of time that it has to move forward as well. When it hits the ground, that's when both motions cease. Okay? All right, now let's answer some other little questions of important things you need to know about this situation. Notice it says, what is the projectile's velocity at the topmost point of the parabola? Well, let's look at it again. Look at all these points. Notice that at each one of these points, the ball has two different velocities. It has an x and a y. And at every point, the resultant velocity is the sum of both of these. And it changes magnitude and direction as the ball travels along the parabola. Okay? In fact, if we put these two tip to tail, we'd get a final velocity that looks like this. All right? So, knowing that at every point the motion, the red, is the vector sum of the blue and the green, let's look at the top. Okay? So what is the velocity at the top? Is it 0? No, only part of it's 0. The other part is not 0. So the net velocity at the top is this. It's just the horizontal component. So right here, we can say, let me use the blue. The velocity at the top is equal to whatever the horizontal velocity is. Okay? In fact, you can show that mathematically, because if you do the Pythagorean theorem, what is the square root of 0 squared plus v sub x squared? Well, it's just v sub x, isn't it? Okay? Now look, what is the projectile's acceleration at the topmost point of the parabola? Well, let's think about this. We said the horizontal motion stays constant because there is no horizontal acceleration. We said the vertical motion changes on the way up and on the way down uniformly by this increment. Does this increment ever change just because you're at the top point? No, it doesn't. So if one acceleration is 0 all the time, and the other is negative 9.8 meters per second squared all the time, then what is it at the top? Oh, well, the acceleration at the top is just the vertical acceleration. Oops, I'm sorry, I didn't see, you couldn't see that. There we go. It's just the vertical acceleration because the other part is 0. Does that make sense? I hope so. All right, now, let's talk about this bit over here for a minute. We said that the horizontal piece stays constant, and the vertical piece decreases by increments of 9.8 and then increases by increments of 9.8, so that when it gets to the ground again, and you've added back those same increments that you originally took away, then the final y component has the same magnitude as the initial y component. So what does that mean for the final velocity? Well, two things. It means that the final velocity has a magnitude that is the same as the initial velocity, but it's at the same angle below the horizontal rather than above. That's the only difference. The y component is now pointed down instead of up, so that changes the angle from above to below the horizontal, okay? Still in the forward direction, but below instead of above. So let's write that right here, okay? Here we go. Watch this. Let me use the other pen. So we're going to say VF, the final resultant velocity, okay? It's equal in magnitude. It equals the magnitude of V sub O, but directed below the horizontal rather than above, okay? It's directed below rather than above. Got it? And don't say it's the opposite direction. Be very careful about that. It's not the opposite direction of V sub O. Look right here. The opposite direction of V sub O would be this way. Now look, those two are not the same, are they? It's not this way. So be careful about saying it's the opposite direction. It most certainly is not, because it still has a forward component. All right? It's directed below the horizontal rather than above. That's how we say it. Okay? Now, last question. The projectile's final velocity is also composed of an x and y component. How are these like the components of the initial velocity? How are they different? Oh, well, we just said that. We said that horizontally, the components are same magnitude and same direction. Okay, exactly the same. But vertically, the components are same magnitude. And now we can say it, but opposite direction, because the initial one points up, the final one points down, and that is opposite. Okay? There we go. Now, let's take a look at an example, because we've covered a lot, and boy, I tell you, there's a lot of ways here you can come at one of these problems. But we're going to take a look at one. In fact, we're going to take a look at one that is very similar to the lab situation that I use, and also similar to some of the virtual stuff that you'll be seeing. Hang on, I'm trying to get myself situated here. All right, so look what it says. On your paper, it says you have a golf ball, and I may need some extra paper, so I've got it ready right here because I don't have a lot of room. And you probably don't either, and we'll probably need it, so you might want some extra paper. Unless the back side of what you printed is blank, and then you can just flip over. It says you have a golf ball, and that golf ball takes 2.85 seconds to travel and land on a flat fairway that's 200 meters away from the tee. Okay, so if it's 200 meters away, that would be the range, wouldn't it? Okay, so it's gone down the fairway, or maybe I shouldn't say down the fairway. Let's say along the fairway, because this would be the range. Okay, that would be the range. This is the time for the motion to take place. That's the time for both motions. Boy, it doesn't seem like we have much information. Well, let's see. Let's make our DVAT chart. Let's look at what we have, all right? So that's the first thing I'm going to do. I'm not going to even bother reading these until I've made my DVAT chart. So we have the horizontal or X side and the vertical or Y side. Okay. D, V sub O, A, T. All right, so here we know the range, start at 0, goes 200 meters. So this would be like your distance or your X sub F. All right, and we also know the time, 2.85 seconds. Well, that's for both motions. Oh dear, we still have a lot of blanks. Oh, but remember, there's some understood information. So let's look back up here and take a gander. All right, here's the first one. The vertical displacement is 0. Where does a golf ball start? On the ground. Where does it end up? On the ground. And it says it's a flat fairway, so we know the vertical displacement is 0 meters. Okay, 0 meters, and I'm going to put a little star by that so you can see that's an inferred piece of information. They're not going to tell you. You have to know that from understanding what golf balls do. All right, now, what else do we know? Well, let's go back up to the picture. Oh, look, right here. Okay, these two pieces of information, the accelerations. All right, so let's write those down. Horizontally, there is none. Vertically, it points down, so we'll put a negative on it, and it's that due to gravity. All right, and I'm going to put a little star right there so we can always see what our inferred information is. I'm not saying you have to put a star on it all the time. I'm saying I'm doing it right now while you guys are learning the differences between this type of parabola and the half parabolas. There's a difference here. Okay, now these were the same on the half parabolas, but on the half parabolas, it was the initial vertical velocity that was 0. It had to start falling. This was not 0. So there is a difference, and this is it right here, okay? All right, so now, there we go. Oh, hey, look, 3 knowns, 1 unknown. 3 knowns, 1 unknown. Hey, we can do this. Now look what it says. Determine the velocity of the ball when it hits the ground. Okay, so what are they talking about? Are they talking about this? Are they talking about this? No, because they didn't say determine the velocity in the horizontal plane. They didn't say determine the velocity in the vertical plane. No, they said determine the velocity. That means this one, the resultant velocity. If they don't tell you which plane, then you can assume they mean the vector sum, the combination, okay? So that's what they want us to know. Well, the only way we can find that is get the components and use the Pythagorean theorem, okay? So we can do that because, look, the components are here and here, and we just said we had enough information. So let's do that. Okay, this component would be from the vertical motion, and we said right up here, x sub f equals v sub o x times t. So that's what we're going to do. X sub f equals v sub o x times t. So if I rearrange that, that's going to give me v sub o x equals x sub f over t. That's going to be 200 meters over 2.85 seconds. And I don't have the answers, so I'm going to have to do this the tough way. So 200 divided by 2.85. You can check